Now we're going to introduce a little abstract reasoning. We're going to use what we know about some specific improper integrals to conclude whether other improper integrals converge or diverge without ever calculating these improper integrals. And this is our main theorem. If f and g are continuous functions and f is always bigger than or equal to g, and both are positive, both are greater than or equal to 0, and f is bigger than or equal to g for any x bigger than or equal to a, then you might say that the integral from a to infinity of g of x should be less than or equal to the integral from a to infinity of f of x if you think of this geometrically with the area interpretation. And then you can conclude that if the larger one is convergent, if the integral from a to infinity of f of x is convergent, then the smaller one must also be convergent. We must have the integral from a to infinity of g of x dx is convergent. And remember, saying that something is convergent means that this integral is finite. So if you have the integral from a to infinity of g of x, which must be bigger than or equal to 0, is less than or equal to something finite, then it must be finite itself. So this makes logical sense. If the integral from a to infinity of the smaller one is infinite, then the larger integral must also be infinite. So if the integral from a to infinity of g of x is divergent, then since the integral from a to infinity of f of x is bigger than or equal to that, it must also be divergent. And this is called the comparison test for integrals. And we'll have something similar when we talk about infinite sums later. And it's very useful if you have something that's difficult to integrate. You can just compare it to something you already know. Here's an example. Suppose I want to figure out if the integral from 1 to infinity of 1 over x squared plus x plus 1 dx converges or diverges. Well, I know x squared plus x plus 1 is bigger than or equal to x squared, so therefore 1 over x squared plus x plus 1 must be less than or equal to 1 over x squared. Now, I know that the integral from 1 to infinity of 1 over x squared converges. It's a p series, which we looked at in previous videos with p bigger than 1. And now by this comparison test, the integral from 1 to infinity of 1 over x squared plus x plus 1 is bigger than 0, but it's less than the integral from 1 to infinity of 1 over x squared dx, which is finite, so it must be finite. And we're only interested here in whether it converges or diverges. We don't really care about its value, so we can conclude it converges. Let's look at another example. Suppose I'm interested in the integral from 1 to infinity of 1 over x minus 1/2. Well, I suspect that this behaves very like the integral from 1 to infinity of 1 over x, so I suspect it diverges. So I'm going to try to compare it to something that diverges. So I'd like to find a function less than it that I know the integral for that function diverges. So I'm going to compare this to 1 over x. X minus 1/2 is less than or equal to x for x between 1 and infinity, and therefore 1 over x minus 1/2 is bigger than or equal to 1 over x for x between 1 and infinity, and therefore the integral from 1 to infinity of 1 over x minus 1/2 is bigger than or equal to the integral from 1 to infinity of 1 over x, which we know diverges. So therefore, our integral, the integral from 1 to infinity of 1 over x minus 1/2 diverges. And of course, both functions here are greater than or equal to 0, on the required interval and satisfy all of the conditions of the theorem.